Alrighty, early math, lesson maybe 59, 60, somewhere in there. And going to add new material. Not an elementary school math teacher, but I do know what kids need to understand at the high school level, or at least I think I do. I got a feeling for it anyway. And I think this discipline has evolved, and I'm trying to follow what I think may have been the history of the evolution of the concepts. It's all guesstimation on my part, but you always have to start with something you know and build off it. I think that's true. So, question number one, perimeter. I've been working with trapezoids, so can you find the perimeter? That's going to be step one. And you pause the video on all of these, and I'm going to call this lesson the rule of four. We're going to do the problems that I have on the front and the back side of the board for 4 straight days. And don't worry about learning it in one. Just roll with the punches and see where you are on day 4. All right, so pause the video on each question I ask, and I'm just going to march my way through it because the first stage of learning is following. And if you ask me how to say desk in Swahili, I'm sorry, but I don't know, and somebody's going to have to tell me. All right. So, what's the perimeter? Well, we're missing a side length. So the question is, can you use what we've been working with, finding that distance? Well, that's got to be 4, right? And if this is 7, and that's 5, and that's 2. And so we're going to get perimeter and area, but first let's get perimeter. All right, so 16 and 4 is 20, so square root of 20. Can you simplify the square root of 20? That'll be question 2. And I don't think I'll make worksheets here, but question 2, square root of 20. Pause the video, see if you come up with the following. Square root of 4 times square root of 5, or 2 root 5. So we'll rename this as 2 root 5. So what's the perimeter? 5 plus 4 is 9, plus 5 is 14, plus 2 is 16, plus 2 root 5. So perimeter equals 16 plus 2 root 5. I can't put those numbers together as they are currently written. So that's the perimeter. And if you want to change that into a decimal, go to Google, type in 2 square root of 5, add it to 16, and you'll have a more familiar length. All right, so now what's the area? Well, the area, you now have a formula, and let's hope that we've been using it. Width divided by 2, so here's your width, divided by 2 times the altitude on the left, and the altitude on the right, which is 5 plus 2, which is 7. So 12 divided by 2, 6 times 4, 24. So that area is 24. All right, what else comes from this? Let's get our sine, because there's an angle here. Okay, and that is actually an arc length right there. That's actually an arc length. Yeah. And it's also kind of what we use to measure degree change, right? Okay, so if you have a circle and we draw a triangle, you're more familiar with that. But if I continue all the way around, the circumference of the circle, where I am on the circumference, if I'm here, works as an angle. So, I want you to estimate that angle. I know that I've got a 2, I've got a 4. You tell me what you think it is. I'll take a random guess, 25 degrees. I didn't give that any thought. I gave it no thought. Okay, all I know is 45 degrees is when they're the same, so I know it's less than 45, and that's all the thought I gave it. But if I want to find out to some degree of accuracy, then I need, well, first off, let's get the sine. The sine, let's call it angle A. All right, what's the sine of angle A? Well, we figured out that was 2 root 5, so it's 2 divided by 2 root 5. And if we want to reduce it, it's 1 over root 5. All well and good. But it didn't answer what the angle is. And for that we have this communication, and you can throw this into your calculator. 1 over root 5, right? Because trigonometry is all about angle to ratio. And it's got to be a way to go from the ratio back to the angle, and you're looking at it. So you're taking the ratio now to find that angle, and I don't have a calculator, I don't use it anymore, and I don't have Wi-Fi, so I can't tell you what that is. So if you want to go and put it in a comment for me, I'd appreciate it. So go to either arcsine or this notation is the same thing, and I'll be talking about that on the back side of the board. So go to an inverse trig calculator, and you'll find these calculations. You plug in 1 over square root of 5, it's going to kick out the angle, because I sure as heck don't know how to get it. Okay, stored information, so you got to access it. All right, so that's the sine. What's the cosine of the angle? Cosine of the angle, 4 over 4 root 5 over 2. Okay, and obviously we can, something's wrong here. What did I do wrong here? 2 root 5, 4 over 2 root 5, sorry. 4 over 2 root 5. I know that the, I know trig isn't going to get me a value bigger than 1. So that was waking up time. All right, so 2 over root 5. And if you go arc cosine and put the ratio 2 over root 5 into the calculator, you better get the same angle. You better get the same angle in degrees or in radians. All right, and radians still could be a big problem. Although we tried to, in the first 58 lessons, tried to get an understanding what a radian is. So if you're just jumping in here, there's been a lot of work done prior to getting to here. We started with trying to understand what a fraction is, so lots happened since then. All right, and then the tangent, and there's also an arctan. There's also an arctan, or tan -1. And I'll be talking about that calculation later. The arctan of 2/4 or a half, that ratio came from angle A, degrees, and angle A in radians. All right, so that's our discussion about that problem. One down, bunch to go here. And then what I plan on doing is weaving these questions into the existing lesson sets, cutting down the number, doing maybe instead of 2, 3, 4 percentage problems, just 1 or 2, so that we can get considerations here. All right, so here's a rectangle. I want you to get the perimeter. And then I want you to get me an equal equation on the other side. Equal equation on the other side, using the same perimeter, but getting the same answers with a square. Okay, it's kind of vague in my, I haven't done this before, so that maybe I can ask that a little better as we go along. All right, I assume, now my grandson's going to say that's 24. Okay, and what's the perimeter? Well, 4 and 6 is 10, and we got another 2 sides, so we got 20 for a perimeter. So we've got to get the same thing over here, 20 for a side length for a perimeter. Okay, and pause the video and see if you can get it. And now we got to make an equal calculation, and you got a marker in your hand, so feel free to do anything you want with the marker, provided you can get equality. I'm assuming you might have said 5 times 5, and that's 25. They're not equal. You got a marker. They are now. And that little manipulation forms a major backbone of the studies that you're going to be encountering as we go up the ladder. So there's real reason for me doing that. All right, so that kind of takes care of that. And after 4 days of practicing this, it's going to morph into something a little more challenging. All right. Just enough of the introduction. Let's get this problem in front of us better. So it's my best rendition of a cube. You know, little ice cube with different dimensions. So let's just look at area here for now. Let's just look at area. So, I'm sorry, volume. Let's look at volume. So 5 times 4 times 6, maybe we're in centimeters. All right, and a centimeter times a centimeter times a centimeter gives us symbolically centimeter cube. All right. And it kind of gives you the feeling for ice cubes. Yeah. All right, so formula, probably know it. Length times width times height, which is nice. And so therefore we have a length. We'll say that's the length, that's the width, and that's the height. 4 times 6, 24 times 5. I'll write that out. 4 times 6 times 5. I just did it in my head, but I think it was 120. Yep, I'd ask you to do the same thing with the cube as I did with the square, but it gets a little more complicated. But there's a connection there too. All right, so what can we call 4 times 6? Let's give it another name. How about the base? Okay, how about the base? So let me get my box. I've got some tissues over here. Here's a box. All right, so we got length times width, and that gives us the bottom of the box. Yep, very nice. It's good to know that formula. So here's my cylinder. I don't know how to draw one. Let me get a can. Let me get a can over here. There we go. There we go. We got a can, and it's got a base too. Yep. So can you give me the volume of that cylinder? Put the can down. Don't have to go all the way back there. Yeah, it's got a round base. And so therefore you need the what? You needed the area of the base to get the cube. You need the area of the base, which is the same as the circle on top, right? And we have studied how to find the area of a circle. Pi r squared, that's the base. And what else? What other dimension does this have? Yeah, height. It has height. So let's say the height is 5. Then the base times the height, which would be 5. So how do you find the area? Well, you need the radius. So I guess I got to supply that. And how about we say that's 2 centimeters? 2 centimeters. I think my grandson knows to square. So 4 pi is the base times 5. So therefore 20 pi centimeters cubed. It's kind of hard to picture the ice cubes in the can. It's easier to think about it in the tray. And so those are some problems we're going to be continuing 4 days in a row. And my suggestion is, see how you feel on day 4. After day 4, see how you feel. And my experience has been a lot different. All right, now let's go to the back side of the board. What's new here? Well, we have these things called functions that we just started in the last lesson sets. So if I said, all right, what's h of 5? What's h of 5? You got these calculations. Calculations have been given names, right, to distinguish one calculation from another. I'm looking at the h calculation. What am I doing in the h calculation? I'm multiplying something times 4 plus 1. It's 5. Looks like h of 5 is equal to 21. That's called functional notation. Well, we've been using these operations called inverse operations to solve equations. Okay, so what's the inverse function of f of x? Well, what am I doing in f of x? I'm adding 3. So you might say, well, what's the inverse of adding 3? You'd be right if you said subtracting 3. But we got to give it a new name because this is a new calculation that's attached to that one. And it turns out we use this notation. That's what we use. Now that's different than what you've been using. -1, you've been using that as a reciprocation in the earlier lesson sets. This has a whole another meaning. Now, you can probably guess or think about a little bit, the history, the evolution of the discipline. When I start my algebra classes, Algebra 1, Algebra 2, or pre-calculus, I always write the same thing on the board. The value of the exponent that you put on top of a 5 to get a 25 is a 2. And I ask students, even students who have studied logarithms to hit pre-cal level, to tell me what I wrote on the board. And they always say 5 squared equals 25. And that's not what I wrote. I said the value of the exponent. That means the word log. Now, we can't do mathematics by writing it out in a sentence. So someone at some point in time used this notation because it's quick and it's simple. F of x, right? And this means the inverse. So what's the inverse of g? I hope you said 2x, because up here you're dividing by 2. The inverse is multiplying by 2. What's the inverse of h? Well, that's a little harder, right? Because then you have to know the order. When you put a number in, right, what's the first thing you're going to do? Multiply by 4 and add 1. Well, if we wanted to go from the number back, we'd have to subtract 1 and divide by 4. So that's kind of hard. That's new. So we have x minus 1 over 4. Now, how do we check them? Well, a minute ago we said f of 5 was 21. I won't do it out again. It was recent enough that I should remember that. So down here, if this is true, then a 21 should get us a 5. 21 minus 1, 20 divided by 4, 5. Well, it's the correct inverse. Now, if all I had was 1, a number here, let's say I have, let's go 29. So what if I had 29? How could I get that? Well, I could plug it in here, but I also could put it right there, because what am I going to do? I'm going to subtract 1 and divide by 4. 28 divided by 4 is 7. Put 29 in. 29 minus 1, 28, divided by 4, 7. So you have had a conversation started. We will continue the conversation in the next lesson set. All right, so that's been introduced. And now I want you just to see if you can name that tune. Or first off, what type of calculation do you have? Do you think there's a pattern there? Can you continue the pattern? Hope so. Hope you can tell me what the next correlation is. Correlation is connecting the x's to the y's. Hope you're saying 8, and I hope you're saying 15. How about this one? Hope you're saying 0, 3. I wish I didn't have those numbers now because of this. Okay, but we'll come back to it. All right, and so it looks to me like if we plot this, we'll call this 0, 3. We'll go over 2 and up 3. That looks about right. That's 3, that's 3. Pretty close. And then we're at 2, 6. And then we're at, let's see, 2, 6. I guess I got to put it on this side. 2, 6. And then we go over 2, up 3. Ooh, and now we're at 4, 9. Shouldn't have to look, should I? And then we're at 6, 12, so on and so forth. Okay, so how do we write the equation of this line? Well, we could do it like Fahrenheit and Celsius to Fahrenheit, because we have a 0, 3, and we know we're going over 2 and up 3. So I suppose we could do over 2 up 3 for x. I guess that's it. Plus 3. Sorry, there are two numbers that are the same. I wish I had changed it, but that's where we're at the moment. And that could be something that works for us. Let's put 8 in. See if we get 15. We've worked now. We know 2 into 8, 4 times 3 is 12 plus 3. Bingo! It worked for this. Now it turns out that you don't always have this nice round number to work with to see different x values work. Okay? But doesn't matter because I'm doing the same thing. I should be able to build off of 612. I should be able to build off of 612, but I'm going to have 6 start as the what? The measuring tape. Time to bring out the measuring tape. Can I find it? Oh, I should have had this prepared. I thought it was right here. Yeah, it is. Right? So if we measure from 0, it's where the tape starts. Okay, I'm at 0. But what if I want to measure from 6? Well, that becomes my beginning. Hit the track. Shoot the gun onto the track meet. What happens? The clocks start. Right? So we're starting the clock at 6:09. You can actually write this equation. Same over up. But I'm going to start at 6. Because 6 minus 6 is 0. And then when I move from 6 to 8, I've changed how many units? 2 units to the right. All right. But if I put 6 in now, I get 0. And that's acting like 0 should. But I want to get what? 12. Now you're being a mathematician. Add 12. That should work for every one of those points. Let's try putting 4 in. 4 minus 6, negative 2. 2 into negative 2, minus 1. What if I take 3 units away from 12? 9. It's working. I'm just putting some things in your head. Now, not all functions are linear. We don't want to get into a linear mindset. So can you plot those values and see what it looks like? And then we'll try to give it a name. Let's call this 1. Then negative 2 is about here. Up 4 is about there. And I'm calling that the coordinate negative 2, 4. How about negative 1, 1? Negative 1, 1 would be about here, I think. Maybe a little bit further to the left. There, I think it's there. I think if we continue the pattern here, 0, 0 is here. 1, 1, 2, 4, 3, 9. Oh, those jumps are different. The over-up jump here is very different than there. Yeah, that's not linear. There's the shape. And that calculation came from what? Pause the video. I hope you said x squared. Well, it turns out we can measure squaring from different values than 0. So can you highlight maybe what value I'm working on right now? Hope you're looking at that. That was a minimum. This is a minimum. So I'm measuring from 5. I'm measuring squaring from 5. Want to give that a go? That's what I did. Let's put 6 in. 1. Let's put 7 in. 4. Let's put 8 in. 9. Let's put the eraser to it. Let's put 2 in. 2 minus 5, negative 3. Okay, so this is what we're going to be doing. I'm also going to be doing some what's minus 4 plus 3 work. We're going to start doing more negative work. And I hope you would say that, okay, let's start at 3 on a number line. I'm going back 4. And I hope if you count that off, you get -1, which is the same thing as the opposite of 4 minus 3. That's also true. Distributing the minus. So we got to start doing some serious work with negative numbers, and that's coming in as well. Okay? Day 1, rule of 4. Let's see where we are 4 days from now.